Welcome to lecture number 3 in stability analysis of slopes. In the previous lecture, we have understood about types of slopes and failure types and causes of slope failures, and then we did understand about infinite slopes analysis and then finite slope analysis by using circular arc method. But we discussed that the demerit of this method is in finding the weight of the entire portion of soil which is subjected to failure and its CG at its location. So, in this lecture we look into the method of slices for which we specifically look Fellenius or Swedish solution and thereafter Bishop's solution. Then we discuss about some stabilization measures which are involved for improving the stability of a slope. So, as we have discussed, a typical pattern of the rotational slides are shown. There are typical failures which can occur. Sometimes a spoon shaped failure which is shown here can occur, and this can have something like a spoon shaped failure where the entire portion will be subjected to a slip in that localized zone, or in sometimes entire road mainly for this man made slopes, the cylindrical shaped failure can occur for the entire section of a slope. There will be a slip surface can form. So, here there is a settlement or a depression from this level, and then a movement with down the movement of the slope takes place. So, in the method of slices, the potential failure surface is assumed to be circular arc with a center of rotation O and its radius r. And how to locate this a critical failure surface, that we look into it later. Now, let us consider a slope cross section having certain slope inclination, and A, B, C, D is the portion of the soil is subjected to say movement. So, here A, B, C, D is the slope portion. Previously in the circular arc method, what we did is that we tried to find the weight area of the entire portion and then multiplied by its weight, but multiplied by its unit weight. However, it is difficult to find its weight and its location. So, one of the other alternatives which is available is to consider dividing into number of vertical slices. Nowadays, even the method of slices is also coming in the horizontal direction. It is called horizontal method of slices, but now currently we will be discussing only the method of slices, that is cutting off the slope portion in vertically. So, here what we did is that this particular portion of soil A, B, C, D is cut into equal widths of the slices. So, here this is the width of the slice horizontally, and then this is the width of the slice, and this is the height of the slice. The assumption is that the weight of the slice is assumed to be act at the center and at the base here. So, this way for this slide, the weight will be acting at the center line of this particular slide. So, h is the height of this slide, and b is the width horizontally, and L is the length along the slip surface. A, B, C is the slip surface. So, the r is this radius. So, this particular slice, if you consider say ith slice, if this slice happens to be ith slice, then its distance vertical weight distance from the center line from the horizontal distance from the O is r sin alpha, and LA is the length of the arc AC, length of the arc AC. Now, if I take the free body diagram of slice ith slice from here, let us consider this particular portion and then represent here, and this gives the forces, various forces which can act on the slice are shown here. So, here this is the slice and having W. So, if this W, if it consists of say number of soils like soil 1, soil 2, soil 3, soil 4, the compound weight can be found out very easily in this particular method. and x1 and x2 are the shear forces which are acting at the interface x1 and x2, and E1 and E2 are these normal forces which are acting on the slice, and alpha is the inclination of this particular this inclined portion of the slice, and n dash and ul, they are nothing but the effective normal force and effective this is pore pressure due to water force. So, now let us consider this method of slices and look into details of the how we can analyze this to obtain factor of safety. So, what we did is that the soil mass ABCD above a trial surface AC is divided by vertical planes into a series of slices of width B. So, what we did is that the slices the entire portion of ABCD is divided into a series of slices of width B. The base of each slice is assumed to be a straight line, it is approximated as a straight line. The factor of safety F is defined as the ratio of the available shear strength tau F to the shear strength tau M, which must be mobilized to maintain a condition of limiting equilibrium. So, the factor of safety Fs is indicated, the factor of safety is indicated as Fs, is defined as the ratio of the available shear strength tau F to the shear strength tau M, which must be mobilized to maintain a condition of limiting equilibrium. So, now considering this, the factor of safety, the definition what we had is tau F by tau M. In this, the factor of safety is taken to be the same for each slice, implying that there must be the mutual support between slides, forces must act between the slices. So, factor of safety is taken to be the same for each slice, implying that there must be mutual support between slices. Now, from the free body diagram, if you look, the total weight of the slice W can be determined by B is the horizontal distance and H is the slice height. So, if gamma happens to be the unit weight of the soil material, suppose if there are say 5 different types of soils with the different unit weights, say gamma 1, gamma 2, gamma 3, gamma 4 and gamma 5, we can determine its composite weight by considering the portions of the soils which are involved in a particular slice. So, with that total weight W can be determined as gamma B into H. The total normal force N, which is nothing but that normal stress sigma into L, includes N dash is equal to sigma dash L and U is equal to UL. U is the pore water pressure at the center of the base and L is the length of the base. So, the shear force on the base T is equal to tau M into L, and total normal forces on sides E1 and E2, the shear force on the sides are x1 and x2. So, once again let us look into the free body diagram, E1 and E2 which are shown here and x1 and x2 which are shown here, and this alpha is that inclination which makes with the line passing through the weight of the slice. So, the weight of the slice is assumed to be center line, and this is located at a distance r sin alpha from point of rotation O horizontally. So, this is that L length along the base of the slice. Now, considering now what we do is that having obtained, so considering the moments of all these forces about O, the sum of the moments of the shear forces T on the failure arc AC must be equal to the moment of the weight of the soil mass ABCD. So, that means that considering the moments about O, the sum of the moments of the shear forces T on the failure arc AC must be equal to the moments of the weight of the soil mass ABCD. So, here sigma TR. So, that means that this T which is acting at this point, this is tangential force T which is shown, and the T and then into this radial distance R, that is the sum of this moment due to the tangential forces, and the weight, if W happens to be weight, W into R sin alpha, that is for the ith slice the moment is W R sin alpha. Similarly, for all number of slices, if you consider, it will become sigma W R sin alpha. So, that is what is indicated here, this has to be equal. Now, from the deliberations in the previous slide, we can write summation tau F divided by factor of safety into L. So, this is written by using T is equal to tau M into L. which is nothing but mobilized shear strength to maintain equilibrium, the shear strength required for to maintain equilibrium into L, which is nothing but tau f, that is shear strength available divided by factor, that is the shear strength of the material divided by the factor of safety into L. So, using this we can write tau f by factor of safety into L is equal to root over the summation W sin alpha. Here R and R will get cancelled. So, please observe. So, now summation tau f by factor of safety into L is equal to summation W sin alpha. So, with this by rewriting we can write factor of safety is equal to summation of tau f L divided by summation of W sin alpha. So, we are left with this expression factor of safety equal to summation of tau f into L divided by summation of W sin alpha. Now, from an analysis, for an analysis in terms of effective stresses. So, that means that under what conditions we need to consider total stress conditions and effective stresses, we will look into these details later. But for an analysis in terms of effective stresses, now we can write factor of safety is equal to summation of C dash plus sigma dash tan phi dash into L divided by sigma summation of W sin alpha. So, here what we did is that this tau f we have written as C dash plus sigma dash tan phi dash into L, where C dash and phi dash are the effective cohesion and effective internal friction of a soil. Now, this can be written as factor of safety is equal to C dash into LA, where LE is the length of the arc AC, which is shown in the previous slide, plus tan phi dash into summation of n dash divided by summation of W sin alpha. So, this is nothing but this is the resting moment and this is the driving moment. So, equation 1 is exact, but approximations are introduced in determining the forces n dash. So, here factor of safety in the method of slices C dash LA plus tan phi dash summation n dash divided by summation of W sin alpha. So, this is equation 1 is exact, but approximations are introduced in determining the forces n dash. So, what we did is that we considered the dividing the entire slope portion into for a considering a trail subsurface. So, what we need to consider a trail failure surface and divide the portion into equal width of slices vertically, and considering the equilibrium of a single slice, and what we did is that we took the moments about O, and based on that we have derived this expression factor of safety is equal to summation tau f into L divided by summation W sin alpha, and substituting for tau f is equal to C dash plus sigma dash tan phi dash, what we did is that we got factor of safety is equal to C dash LA plus tan phi dash summation n dash divided by summation W sin alpha. Now, for this method of slices is extended further by the Fellenius or Swedish solution. In this, it is assumed that for each slice the resultant of the interslice forces is 0. So, here what we did is that what Fellenius assumed is that for each slice the resultant of the interslice forces is assumed as 0. So, the solution involves resolving the forces on each slice normal to the base, that is n dash is equal to W cos alpha minus U alpha. UL. The solution involves resolving the forces on each slice normal to the base as n dash is equal to W cos alpha minus UL. So, now substituting for n dash as W cos alpha minus UL in the previous equation which we derived, rewriting the equation 1, factor of safety can be written as C dash LA plus tan phi dash summation of W cos alpha minus UL divided by W sin alpha summation. So, this we look into further in the form of a figure. So, here the Fellenius or a Swedish method of slices which involves, so here a particular slope portion which is shown and is assumed that is divided into 7 number of slices vertically. The entire portion A, B, C, D is divided into 7 number of portions vertically, and what we did is that this particular portion of slice at its CG assumed that its weight is acted. So, for this from this 2/3 distance from here, the CG of this weight of this slice is assumed to be acted. Then for all these analyses, as we discussed earlier, the per meter or per unit length is considered. So, here the weight is nothing but area of this portion into one unit, that is 1 meter, into the unit weight. If happens to be gamma, then you will get the weight of this particular slice per meter length. Similarly, this slice 2, slice 3, like that. So, we get W1, W2, W3, W4, W5, W6 and W7. So, after having obtained, so this when this is marked to a scale, then by drawing the lines to the assumed center of rotation, we can measure alpha 1, alpha 2, alpha 3, alpha 4, alpha 5 with vertical. So, this vertical is nothing but the line of direction of this weight force for a particular slice. So, here the alpha 1 is shown here alpha 3 is shown, alpha 4 minus alpha 5, here observe that it changes signs. So, the components of W cos alpha and W sin alpha can be determined graphically for each slice. So, for an analysis in terms of total stresses, the parameters Cu and phi u are used and the value of u is equal to 0. That means that assuming that Cu and phi u are considered for the total stress condition, that indicates that undrained condition. So, for the case of undrained condition, we can write factor of safety as Cu into LEA, that is nothing but we can use this for LEA is the length of this portion, total length of this portion, Cu into LEA. Otherwise, when you have got each slice, when you assume that this is the length, then the L1, L2, L3, L4, L5, L6, L7 forms this LEA. So, Cu into LEA plus tan phi u summation of W cos alpha divided by summation of W sin alpha. For phi u is equal to 0, that is for purely cohesive soil slopes or saturated clayey slope. In that situation, for phi u is equal to 0 condition, when this term gets cancelled, what we have the factor of safety term is, factor of safety is nothing but Cu into LEA divided by summation W sin alpha. This will be nothing but the whatever we have discussed for in the previous lecture about circular arc of analysis. The only difference is that the soil which is same, but under undrained conditions, but we divide this entire portion of the slope into number of vertical slices and then we determine the factor of safety. In such situation, the factor of safety is nothing but Cu into LEA divided by summation of W sin alpha. Now, this was further extended by Bishop and this Bishop's method of slices, it is known as the Bishop's method of slices. The previous method which we discussed is known as Fellenius method of slices or Swedish slip circle method or Swedish method of slices. So, in this solution, it is assumed that the resultant forces on the sides of the slices are horizontal. So, in this Bishop's method primarily, it is assumed that the resultant forces on the sides of the slices are horizontal, that is x1 minus x2 is equal to 0. So, for equilibrium, the shear force on the base of any slice is, we can write T is equal to 1 by Fs into C dash L plus N dash tan phi dash. So, resolving the forces in the vertical direction, that means that considering again the forces in the with this equilibrium of this particular expression, this particular free body diagram of the slice I, we get W is equal to the weight of the slice N dash cos alpha plus UL cos alpha plus C dash into L divided by factor of safety sin alpha plus N dash by factor of safety tan phi dash sin alpha. After some rearrangement and using L is equal to B secant alpha, we can write factor of safety is equal to that is submitting some after some after putting here factor of safety is equal to 1 by summation of W sin alpha summation C dash B plus W minus UB tan phi dash secant alpha divided by 1 plus tan alpha tan phi dash by factor of safety. So, if you look into it, the factor of safety term involved in both the both left hand side and right hand side, this indicates that it requires iterations. So, many for this manual calculations will be difficult, but the manual calculations are possible for Fellenius method of slices. Even manual calculations are possible if the soil strata is having say up to 5 number of soil layers. But for the Bishop's routine solution, considering the involvement of the iterations, the computer program is recommended, but Bishop's routine solution can be calculated first estimating the factor of safety by using Swedish method of slices or Fellenius method of slices, and iterating that to with a convergence to get a factor of safety by using Bishop's routine solution. So, the expression for the Bishop's routine solution is factor of safety is equal to 1 by summation W sin alpha summation of C dash B plus W minus UB tan phi dash secant alpha divided by 1 plus tan alpha tan phi dash by factor of safety. In the Bishop's routine solution, Bishop 1955 also showed how non-zero values of the resultant forces x1 minus x2 could be introduced into the analysis, but refinement has only a marginal effect on the factor of safety. So, Bishop 1955 also showed how non-zero values of the resultant forces x1 minus x2 could be introduced into the analysis, but refinement has only a marginal effect on the factor of safety. So, the pore water pressure can be related to the total fill pressures at any point by means of dimensionless pore pressure ratio. So, which is also known as pore water pressure coefficient or pore pressure ratio. Here the pore water pressures can be related to the total fill pressure at any point by means of dimensionless pore pressure ratio or pore water pressure coefficient, which is given by gamma u is equal to u by gamma h, where h is the fill height, gamma is the unit weight of soil, and u is the pore water pressure at that particular point. So, if the gamma u is equal to 0.5, that indicate the slope is completely saturated. If it is approximately about 0.5, the slope is assumed to be saturated. And by putting this for any slice, gamma u is equal to u by w by b, and by rewriting the equation which we derived in the previous slide, that is this particular equation, we get factor of safety is equal to 1 by summation w sin alpha summation c dash b plus w into 1 minus ru tan phi dash secant alpha divided by 1 plus tan alpha tan phi dash by factor of safety. So, here this particular ru considers the effect of the pore water the phreatic line within the slope. So, if the phreatic line is far away from the slope, say for a road embankment constructed on a foundation soil, in such situation if the groundwater table is far away from the slope section, so we can assume Ru is equal to 0. If it is assumed that Ru is about partially submerged, then Ru a specific value for Ru can be given, or if the phreatic line is estimated within the dam or any slope cross section, then the phreatic line can be dictated. So, with that given condition, we can obtain what is the factor of safety of a given slope. So, what we looked into is that two methods of slices, basically the development of method of slices, and then for that Fellenius and Bishop's solutions were given. So, in all these things, it is very important to locate a critical failure surface. The critical failure surface is the one which gives the lowest factor safety. So, for which the slope will be said to be stable. In the modern advent of the computers and with availability of programs, a number of options available for locating a critical failure surface, and the options involved the automatic generation of circles or failure surfaces based on the initial input values, or one can specify the point where the circles have to be located physically. So, based on that the number of failure surfaces can be generated. Once it calculates the factor of safety of all these failure surfaces, and the efficiency of the program depends upon the one which actually gives the correctly the lowest factor of safety. That happens to be the possible failure surface which can actually occur and for a given section under analysis, for a given section which is being analyzed. But there are earlier methods which are put forwarded. The one of the methods is that the Fellenius empirical method for toe failure. This method what it is done is that for a given slope cross section, say if a cross section is there and if the slope inclination is beta, then then what we do is that if h is the height and so locate a point from locate a point that is at a distance 2h from this particular point, and from this point at a 4.5 h you locate a point here and join this point through this slope, and along this slope if you draw number of circles, suppose this is center 1, center 2, center 3, center 4, and what will happen is that the factor of safety decreases and then factor of safety increases. So, once that happens, the one which actually gives the lowest factor of safety. So, here what one can do is that one can generate grid of centers and number of slip surfaces can be tried. The one or the one can draw the contours which are actually having which gives the factor of safety, and the one which gives the lowest factor of safety is actually identified as a critical failure surface. In this method, an empirical method where for beta is equal to 60 degrees, this alpha is equal to 29 degrees, psi is equal to 40 degrees. With that we can locate this particular point, and then that is the one of the critical failures. With that we can draw a circle. Similarly, for beta is equal to 45 degrees, alpha is equal to 28 degrees. Along this line, if you draw, then we get alpha is equal to 28 degrees, psi is equal to 37, and beta is equal to 26 degrees. That is the almost flat slope, 1 vertical, 2 horizontal. That is alpha is equal to 25 and psi is equal to 35 degrees. So, this is one of the methods. For example, if this is a base failure, like location of critical failure surface for a base failure, where a circle passing through the entire foundation soil as well as to the field material. In this case, this can occur because as the this failure surface cannot penetrate through the rigid stratum. So, it will be tangential to this. So, at a if this slope distance is marked and a horizontal distance is say b by 2 and b by 2, what we can get is that at a distance b by 2 and b by 2, if you locate a line along this line, if you draw a line and take set these points x1 and x2 such a way that the angle is around 133.5 degrees. This is assumed to be with this process, if you are able to construct a circle, and that is assumed to be a critical failure surface, which is actually a tangential to this. The condition is that tangential to this, and then so with that conditions you once you draw the circle along this vertical line, that one will give the critical failure surface. So, we try to look into this procedure for very empirical procedures which are available for locating critical failure surface. Now, having looked into it, this particularly this stability analysis which is required to be carried out for short term and long term conditions. So, short term stability basically this is carried out for low permeability soils where the drainage is not permitted, and long term conditions where the drainage can occur, fully drained stage can occur. In that case, C dash and phi dash parameters are required to be used. So, effective or total stress parameters, the short term low permeability soil, that is example clays, at the end of construction the soil is almost still undrained, hence the total stress analysis making use of the undrained shear strength is used, and the free draining materials like in case of sands and gravels, the drainage takes place immediately, hence the effective stress parameters C dash and phi dash are used. So, in the long term, after a relatively long period of time, the fully drained stage would have been reached. Hence, the effective stress parameters C dash and phi dash are used. So, this is based on this judgment, one can perform either effective stress analysis or total stress analysis for the stability of a particular slope under consideration. Now, let us look an example based on the whatever we have discussed about the Fellenius method of slices or Bishop's method or Swedish method of slices. Here a slope with certain cross section is shown and with a pore water pressure data, and this is location of the tension crack, that is jet C is the tension crack, which is based on this 2 C by gamma, which is estimated here. So, with that, this is the tip of the tension crack. Let us assume that the slope is divided into 7 number of slices, 1, 2, 3, 4, 5, 6, 7, and having these are the horizontal widths of the each slice, and is located the circle is located like the procedure whatever we have discussed just now, with 4 meters and 4 meters is the horizontal distance. So, this is the central line. So, with that point, and when this angle is about 133.5 degrees also, this particular this surface is located. And here what we have is that we have got the soil which is within the embankment portion is having gamma about 18.5 kilonewton per meter cube, psi dash is equal to 20 degrees, C dash is equal to 15 kilonewton per meter square. And in this case, foundation soil gamma is equal to 18.5 kilonewton per meter cube, phi dash is equal to 25 degrees, C is equal to 8 kilonewton per meter square. So, this is the properties of the foundation soil, and this is the properties of the soil within the bud. So, 2 layers are there. That means that up to this portion, this base of the slice is exposed. So, this is the soil portion which is existing here as well as here. So, we need to consider in this zone these properties, and below this portion we have this another soil which is having C is equal to 8 kilonewton per meter square and phi dash is equal to 25 degrees and gamma is this much. So, these properties have to be considered. So, by drawing now this each slice, we can calculate weight W1, W2, W3, W4, W5 and W6 and W7, and in this gamma 1 and gamma 2 is considered for arriving at weight 3 in this portion. Similarly, weight 4 is considered by using this particular procedure. So, here so happened that gamma is same for both the soils which is given here. This distance, vertical distance is 7 meters for the center of rotation and 5 meters is the height of slope. So, when we plot this T and W, W is the weight of the slice. So, the force diagrams are shown here. This is for the first slice, second, 7th slice, 6th and 7th are these slices. So, you can see that this is the portion where only the W is acting, the other portions remain, that components are 0. Then L is equal to B secant alpha. Now, let us tabulate the results what we got from this particular analysis in this form of a table. So, Fellenius method of slices, here being the effective stress, factor of safety is equal to summation C dash L plus tan phi dash summation n minus UL divided by summation T. So, in the slice we have divided into 7 number, and weight of each slice is determined by measuring the graphically the weights. Here this portion, this is considered as a trapezium, this is considered another trapezium, and this weight is determined. Similarly, this portion, like this the other remaining slices also considered. Having done, these are the properties that has been considered, and this is the tan phi dash for up to these 2 slices have got different properties, and these slices entirely lying on the second soil, that is the foundation soil. Then these are the length of slice along the length of the base along the arc. So, this is given here, which is nothing but B secant alpha, and B is the horizontal distance of the slice. The horizontal distance are shown in the previous slide. Now N is equal to W cos alpha, T is equal to W sin alpha. These components which are shown here, W cos alpha is this component and W sin alpha is this. This is the one which causes the driving moment. Now, C dash L is obtained, C dash and then multiplying that we get L, and UL depending upon the periodic line location with multiplying with the heights of the slices, we get this UL in kilonewtons. Then N minus UL we get this, and N minus UL tan phi we get summation as 267.5. Similarly, if you summation of T we get summation T we get 239.4, and summation of the C dash L we get summation of C dash L as 158 kilonewtons. Now, substituting in this equation C dash L, that if you substitute, that is 158, and the summation of this particular thing 267.5 into that summation of this into into n minus UL tan phi is given here. So, that is nothing but 158 plus 267.5 divided by 239.4, that is summation of the W sin alpha, that is summation W sin alpha, that is summation of T, which is 239.4, which yields the factor of safety 1.78. So, there are like the factor of safety is equal to 1, it indicates that the slope is under the wedge of failure, but the convention for the static loading conditions, the factor of safety which is adopted nominally for the working stress conditions is about 1.5. If you consider the 3-dimensional effect of a slope according to DIN code, it is about 1.4. But there are different conditions, loading conditions like earthquake loading and other conditions demand different factor of safeties, but conventionally a factor of safety of 1.5 is adopted under working stress conditions. But if the factor of safety is less than 1, that means that the slope would have already failed. The factor of safety is equal to 1 means it indicates that the slope is on the verge of the failure. Sometimes while analyzing the already failed slopes, one can also obtain by back calculating the shear strength parameters of a particular soil. So, this particular method is called back analysis of a slope. So, based on that one can perform the back analysis, and by fitting a failure surface passing through the tension crack which was observed on the verge of the failure also. So, with that we can obtain the factor of safety for a given factor of safety of 1, what is the say if this factor, if the failure occurs under undrained conditions catastrophically, then we can obtain under total stress conditions what is the undrained cohesion which is available. So, this can give some extent a shear strength parameters. So, those parameters are called back analyzed parameters and can be comparable to the laboratory parameters. Now, having looked into it, this is how the Fellenius method of slices can be adopted. So, in case if the soil is having say more than 3 or 4, and if it is required to be adopted by using Bishop's method, then computer programming is required, and which is for this standard codes are available, and based on that analysis can be performed. Now, having discussed about the method of analysis of the slopes and causes of the failures of the slopes, and we also require to consider what are the avenues available for stabilizing a slope. There are many options which are available for stabilizing or reinforcing the slope. There can be, the slopes can be natural slopes or man-made slopes. Sometimes these slopes are natural slopes or hilly terrain slopes which require stabilization. So, different types of techniques are available. Sometimes for the sake of construction of steep slopes in urban areas, so the slopes are initially strengthened by using certain reinforcement layers. So, that is called reinforced earth slopes also in urban areas which are possible. But if there is a existing slope which has been investigated and found out that is required to be stabilized, then many methods are available. So, one of the options which is available is the regrading, that is removing the unstable portion and increasing the stability of a slope, that is flattening of a slope also. Or another avenue is that subsurface and surface drainage. The drainage is very important aspect in this slope stability. So, that is required to be considered, and retaining walls, that is particularly at the toe walls, and they can be considered as a remedial measure for enhancing the stability of a slope. But if the failure surface is passing beneath the slope, then the retaining wall, retaining the slope with a wall is also in danger. In such situations, methods like pile stabilization, that is discrete or vertical piles, discrete or staggered piles with or without connections, can be considered for stabilizing a slope. So, in this method what will happen is that the load is transferred, load which is actually arise due to moving soil mass is transferred to the piles into the deeper stratum. that is this method which is discussed here, discrete vertical piles, and this method can be adopted for new construction or to the existing, suppose if there is a soil slope, predominantly soil slope, so there it can be used for stabilizing the existing slope. Another technique which is gaining momentum in the recent past is soil nailing. So, in this technique a certain steel bar or a of certain diameter is drilled into a pre-driven hole, and then with spacers, and then the portion is grouted, and then once it is grouted, the rod, extended portion of the rod outside is connected, and so with the frictional interaction between the grouted portion and with due to tension in the nail, and it will try to give the stabilizing effect to the slope. Then another aspect is geosynthetics, and recently the vegetation or biotechnical stabilization is gaining momentum. So, in this slide what we try to understand is that different options which are available for stabilizing slopes. One is regrading, second option is subsurface drainage or surface drainage. Subsurface drainage to get rid of the pore water pressures within the slope, and surface drains to prevent erosion failures of slopes and making flat slopes steeper, and then can cause to the failure. So, this surface drains will allow the erosion to be kept under control. Similar retaining walls, discrete vertical piles, and soil nailing, and geosynthetics and vegetation. And some of these slopes can be adopted, some of the techniques which are there can be adopted to the existing slopes or in situ slopes, and some of the structures can be, some of the techniques can be adopted only for some slopes which are required to be constructed. Particularly the slopes like geosynthetics with horizontal orientation. So, in the regrading, so here the slopes which are flattened, this is the original slope. So, this is the revised slope cross section is shown. That means that here by removing this portion of the soil, then what will happen is that the factor of safety of a particular slope cross section increases. So here this is the removed portion, and this is so here by removing this particular portion of a soil, and that means that this particular slope is now like benching. So, provision of a berm or a benching for slopes also is thought to be one of the remedial measure where for increasing the factor of safety. In this case, what will happen? The slope will tend to behave like a two slopes, one is here and one is here. With that, this is the new slope surface after removing this particular portion of the soil. So, benching technique, which is also as a regrading or a flattening technique, which actually increases the factor of safety of a particular slope, which actually works out as one of the simple option for considering or improving the performance of a slope. Or regrading, a berm provided at the toe, which increases the factor of safety, and protection against the erosion at the toe. For example, if this is the zone susceptible to erosion due to wave action, or and if there is no protection, then it can be subjected to a slip circle failure. This is the zone which can, in case of no protection, a failure can occur. So, if there is a gravel or rock fill is provided, which actually increases the factor of safety and acts as a protection for the slope against instability. So, regrading or unloading is a technique to reduce the driving forces within a sliding mass. The two methods for the regrading are excavation and lightweight fill. So, the two methods what we discussed are that excavation and lightweight fill. So, regrading or unloading is a technique to reduce the driving force within a slide mass, and the two methods for regrading are excavation and lightweight fill. Now, here which is shown, another option is that this portion of the slope was cut, removed, and then provided here, which actually makes the slope flatten slightly. Lowering of groundwater to reduce pore pressures in the slope. So, that is nothing but the portion for drainage of a slope. Here interceptor ditches for diverting the surface slope they surface flows, that actually helps here, and these are the collector drains with perforated pipe in gravel filter and lobe. So, collected water can be discharged below the toe by utilizing the manholes connected to transverse drains. So, this is water table before before draining, and this is the lowered water table with the help of this. So, when the water table which is kept under control, so the pore water pressures within the slope under control, so that effective stress are maintained. So, with that what will happen is that the slope stability increases. So, the lowering of the groundwater table to reduce the pore water pressure in the slope is another option, which is actually done through surface intercepted ditches or collected drains within the slopes. So, drainage reduces the destabilizing hydrostatic and seepage forces on a slope, as well as the risk of erosion and piping. So, it can be surface drainage and subsurface drainage. So, the drainage phenomenon which reduces the destabilizing hydrostatic and seepage forces on a slope, as well as on the risk of erosion and piping. And plan for building design to aid slope stability. Suppose if the building design is made like this, if at the crest of the slope a building is constructed, and similarly at another building is constructed at the toe of the slope, the shallow foundations are basement for the building are below the toe, and deep foundations are basement for the building on the top of the slope. So, if this occurs, then what will happen is that if the planning is done like this by locating the building at this different elevations, this actually enhances the slope stability. And here typical surfacial slope failure in highway embankment is shown after Loher et al. 2002. You can see that for a transportation embankment or highway embankment, how that a typical slope is subjected to. This is the embankment, and where the slope is subjected to a surfacial slope failure. So, here what they have adopted is that for improving the stability of the slope, recycled plastic pins were used, and then it was stabilized by driving into this slope. So, what happened is that this unstable portion was retained by driving recycled plastic pills into the slope. So, the cross section is shown and a fade area. So, the entire area is actually strengthened to prevent this slope. So, this one after installation of this, so by using this this slope was being stabilized, you can see in this portion. So, you can see that the improvement which actually reflected in this particular slide. The another method is to the gabion walls for slope stabilization. In this technique, what is done is that these gabion walls are nothing but is a wire meshes which are predominantly made with mild steel, which are coated with anti-corrosive elements. So, and in this if the area is actually having abundant availability of stone, the stone is actually filled in these cages and placed one by one above the other, and with that actually this type of walls can come. So, advantage and merit of this gabion wall is that being freely draining materials, the water can seep through this one, and also because of the gravity or the self weight, they also ensure the stability and behave like so. And because of this iron cages, you can have steepness as close to 90 degrees. So, the gabion walls applications is actually even catching its momentum in India also. Now, another technique which is conventionally used, but we never looked into details, but this technique which is picking up in the recent past, which is called biotechnical slope stabilization, or this is a part of bioengineering, where here live brush layers were used for stabilizing the slope. So, this is the cross section is shown, and this is the plan view of the. So, the presence of these when these brush layers are planted with a planned layout and all, and with that what will happen is that the stability of this particular structure. So, these elements which are penetrating or embedded into the soil act like a reinforcement elements and enhances the stability. Several laboratories which are involved in investigating and developing techniques for biotechnical slope stabilization, and the detail is beyond the scope of our lectures, but this is a technique where which has got also aesthetic look as well as the technical advantage with the biotechnical stabilization, and also a environmental friendly technique. So, another application for stabilizing slopes is that wraparound geotextile reinforced slopes, or you can also have geosynthetic wall with geosynthetic slope with a facing. So, in this case a wraparound geotextile reinforced slope is shown, and with after about certain time you can see how that green aesthetic view of the look. So, this type of techniques can mingle well with the environment. So, this is another type of slope stabilization technique which can be used for retaining this, and which also is gaining momentum in its application. The another technique which has been discussed is the schematic a nailing technique. So, in which what is done is that nails of certain diameter with certain layout, horizontal spacing and vertical spacing are driven into the soil with certain inclination alpha. Generally, it is driven at between 10 to 20 degrees inclination, and use this pore water pressure. So, if this value is u by gamma z is equal to u is equal to gamma w z, if this u by gamma z is equal to 0.5, then the slope is said to be completely saturated. So, L is the length. So, for the stability point of view, a minimum requirement of about 0.8 to 0.9 times of the L is required. So, the mechanism here is that if this is the active zone and this is the resisting zone, what you can see is that with a nail with certain inclination, the frictional interaction between the nail and soil and the soil structure interaction between the facing and wall contributes to the this stability. So, you can see that in the active zone, this portion is trying to be pulled out and this portion is trying to pull inside. So, this because of this outward shear stress tend to pull the nail, but this is being resisted by this embedded depth. So, it requires a certain length so that it can actually generate this particular forces in the resistant zone. So, what we did in this particular topic, we have reviewed type of slopes and failure types, causes of slope failures, and we also looked into analysis of infinite slopes and method of slices, and we used circular arc method of analysis and Taylor's method we have discussed based on for undrained conditions, and Fellenius method and extension of Bishop's and stabilization measures we have discussed. So, with this we come to the end of the stability of the slopes, and where we have discussed about the analysis methods as well as some example problems, and also different avenues available for stabilizing slopes. In this slide, some of the references which are used in the development of this course material are given. This is Peck Hansen Thornburn, Foundation Engineering, and Tarjagi, Peck and Mesri, this is Soil Mechanics and Engineering Practice, and Das, Advanced Soil Mechanics 1987, Scott, Introduction to Soil Mechanics and Foundations 1980, and Dunn, Anderson and Kiefer, Fundamentals of Geotechnical Analysis 1980, McCarthy, Essentials of Soil Mechanics and Foundations, Basic Geotechnics 1982, the Barnes, Soil Mechanics, Principles and Practice 2000, Craig, Soil Mechanics 1992, and Gulati and Datta, Geotechnical Engineering 2005, Buddhu, Soil Mechanics and Foundations 2000, Holz and Kovacs, Introduction to Geotechnical Engineering, and these books which are recommended for further knowledge in this particular subject area. So, these references are once again shown, which is in this first slide, and these references are not arranged in alphabetical order. These are the references which are given in the first slide and second slide and in the third slide. So, as you see in this slide, the soil mechanics learning is a continuous learning process. So, which involves the commitment and interest in this particular subject.